I'll explain the Lab2 lab sheet in this video. The aim of this lab is to write our first OpenMP program and also write some non-trivial OpenMP programs. In fact, some of the OpenMP constructs that we'll use in this lab are quite powerful in the sense that almost any C program can be parallelized using these quite a few simple constructs. Now, today's lecture I have explained what is hyperthreading, and most probably in your lab machine hyperthreading will be enabled. And also if you are doing this lab in at home, then hyperthreading could be enabled in your machine. You can turn off hyperthreading, and you'll find in the first bullet point in this lab sheet there is a link from where you can turn off hyperthreading if you are using Linux machine. If you are doing your labs in Visual Studio on the Windows platform, then there could be other instructions that you can search on the internet to find out how to turn off hyperthreading. But this lab is not about performance so much. So if hyperthreading is enabled, it's all right for us, and we'll just see how multi-threaded programs work and how to time those programs, etc. First thing that we'll learn is how to parallelize a block in a C program. Namely, we'll use first the pragma. All OpenMP directives start with a pragma, #pragma, and we'll first learn how to use pragma OMP parallel. Now, this discussion that I am recording right now is kind of complementary to today's lecture. For example, in today's lecture, we have discussed how to compile OpenMP programs. And also I have mentioned that along with other include files that you do include in your C code, you have to include this particular header file called omp.h. And the compilation command is also in the lecture note for today's lecture. You can look that up. Now the first thing is to what is really happening when you use something like in a C code. I'm not writing the C code, but I'm just writing some part of the C code. So you have a pragma OMP parallel, and then you have a block. And that is the first thing you have to do. You have to write a multi-threaded program in which each thread will write its thread number and some meaningful message. We have discussed this program in the lecture today, and you can look up the lecture note, and you have to add just a few lines to write this program. Now, what really happens is, if I may draw a picture here, ordinarily when you write C code, you have a single thread of execution. That is, execution proceeds, I am just drawing it, okay, I'll draw it vertically. So execution proceeds from top to bottom, assuming that there are not any if statements in your program. If there are loops, then execution goes around the loop again and again, but eventually comes back and proceeds sequentially. But in parallel code, or when you are using the pragma OMP parallel, so here is our code again, pragma OMP parallel, and some block where you are printing something like the thread number, etc. So here what happens is there is a master thread as before, as it happens in the C, any normal C code, and then as soon as the pragma OMP parallel directive is reached, that master thread spawns many other threads depending on how many threads you want. In OpenMP, you can specify how many threads you want, or if you don't specify, depending on how many cores your machine has, those many threads will be created. So all these threads then continue execution and until the end of this pragma block, and then all of them sort of die or they complete their execution, and again the master thread proceeds. So you can get the picture that whenever there is a pragma OMP parallel, there will be multiple threads, and as soon as that block is complete, then there will be again only one thread in the program. So that's the first exercise. The second bullet point in your lab sheet, where you are supposed to write a program where you print some meaningful message. And also after that, in the third bullet point, you have to modify the program so that one or more threads sleep for some time. This is also discussed in today's lecture. So you have to use the sleep and one in parentheses for making any of the threads to sleep for 1 second. Now you have to time your program, and I have given in the lab sheet in the third or fourth bullet point. In the fourth bullet point, I have shown you how to print the amount of time spent by the program. If you just time your print statement, the program that has print statement, the program will run so fast that almost always you will get a time like 0 point many zeros like this. So we have to make our program to work, and before going into that, in the next bullet point, you have to write a C program where you will change the number of threads used by OMP set num threads directive. You can see the syntax there. You have to just replace the n by an integer, and OMP or OpenMP will spawn those many threads. Now this directive should appear before the pragma OMP parallel directive, so that before the master thread can spawn the threads, we have all those threads, which the number of threads that we require. And as I have told you, if there is no OMP set num threads directive, then the number of threads will be equal to the number of cores. That includes both physical and logical cores. Now afterwards, when you write that, afterwards we have the next task that you have to do is to just change the number of threads by changing the integer n and see how your program executes. And the next task is the most important, where you have to parallelize a for loop using pragma OMP for directive. I have given the skeleton of the code, and you have to use that skeleton for writing the for loop. Now what I have asked you to do here is to write a program that adds floating point numbers stored in a large array. This is our first non-trivial OpenMP program. Each thread will use a local variable called local sum, and it will compute its own part of the for loop, and so we have to make the local sum a private variable. Now something to note here is in pragma OMP4, pragma OMP4, what really happens is if you have a loop inside that goes from, let us say, I equal to 0, I less than n, I plus plus, and there is some loop body. Now what really happens is this range that is 0 to n, let us say this is 0 and this is n, depending on the number of threads that are available to the compiler, because either you have specified the number of threads you want or the default number of threads. depending on that, this range will be divided into n parts. So for example, this range here I have shown this range is divided into 1, 2, 3, 4 parts. It's not always equal division, but the thing to remember is there will be, as if there will be, if there are 4 threads in the system, there will be 4 independent for loops which will be executed each by one unique thread. That means this part of the for loop 0 to, let us say, n over 4, 0 to n over 4 will be executed by one thread, n over 4 to n over 2 will be executed by another thread, 3n by 4 will be executed by another thread, and the remaining will be executed by the fourth thread. So you have to keep that in mind. And another thing you have to keep in mind is if you use anything, let us say we have a pragma directive here, pragma omp for, and I equal to 0, I less than n, I plus plus, and here you have a variable called local sum where you want to store the result of adding the numbers locally in some variable. Then this variable local sum must be a private variable for each thread. If it is a variable that is shared by all the threads, anything that has been declared here will be shared by all the threads. You have to remember that whenever a thread is created, the thread has access to all the variables of its parent. And hence, whenever you declare something in the program, that is common to all the threads. So if you want threads to have some local variable that they independently and uniquely they can modify, then you have to declare that through the private clause. So private sum local, local sum or something like that, if your variable is called local sum. So you just write this code and use large arrays by increasing the array size and filling it up with random floating point numbers that you have done already in the first lab. Beyond a certain array size, you will get an error, but you can just try and see. We haven't discussed dynamic memory allocation, so we can't use really malloc, but you just increase the array size until the point when you get a runtime error. Time your program. And the very last bullet point, I have asked you to do something intensive, compute intensive, so that we can really get some meaningful timing out of our program. What I have asked you to do is to write a OpenMP for loop as before, as I discussed before, and inside this for loop, to make it compute intensive, call a function called sort. The sorting program that you have written in the first lab will come handy here. Perhaps you wrote the sorting program in the main function itself, but now you can change that to another function and called sort and pass this array which you can declare here. Pass that array to the sorting program. So every thread, in other words, will execute this part of this for loop, and suppose this for loop is from I equal to 0, I less than 1000, I plus plus. If you have 4 threads, each thread will execute this for loop 250 times and call this function sort 250 times in that loop and sort it. Now, what is the purpose of that? There is really no purpose other than to make the threads do some significant amount of work. And you should write appropriate timing code that you know from the first lab to see how the time taken by your program is increasing when you increase the size of this array, or even you increase the number of iterations of this for loop. So that is the lab sheet in brief, and you can ask me any question. I'll be in my office, or if you if I'm not in my office, I'll come to the lab in the beginning, and later on you can post on the help forum or ask on Facebook, whatever is your preference.